Okay, up next we have Pranav Agrawal from the University of California, Los Angeles, and he's going to tell us a little bit about how attaching hydrophones to fire hydrants can help detect water leaks. So,
Thanks for the introduction, Ashley. Good morning, ladies and gentlemen. My name is Pranav Agrawal, and I'm a postdoc at UCLA. I'm working with Professor Sriram, Narasimhan, and with my collaborators at Digital Water Solutions in Canada. So what comes to your mind when you hear about water leaks? Some sound coming from the tap or from a pipe joint, right? These are the small leaks, but if these leaks are not treated properly, they might actually result in big bursts. The picture that you see over here is from UCLA in 2014, where a 30-inch water main broke and around 8 to 10 million gallons of water was lost in around 4 hours. It flooded classrooms, athletic fields, and the famous Poly Pavilion. So this keeps on happening, and it's not the only one. One of the pictures over here is from Florida recently in February. According to estimate from American Society of Civil Engineers, approximately 6 billion gallons of water is lost every day in the US, which is approximately, giving a different context, it's equivalent to filling 9,000 swimming pools. And yes, we are talking about each day. In a different context, 30% of the treated water is lost every day, and it doesn't reach households. But the problem over here is a bit different. What we see over here is on the ground, right? But a lot of things, majority of the things actually happen underground, where these water distribution networks have minor leaks, and a lot of water actually just seeps down, and it remains undetected for months or sometimes actually years. Why do we have leaks? So majority of the water infrastructure system was actually built in 1970s, and a lot of it is cast iron based. So corrosion is a problem. And then we have water hammers. Water hammers are basically the pressure transients, which gets developed in the pipe system when you close a wall. So there's a pressure fluctuation, and then the loose ends, or there could be some parts where the leaks might occur. And then there are some environmental factors, and there could be accidents due to the construction. There has been a lot of research in finding the leaks, but why is it so difficult yet that we don't have a proper solution to find a leak? So over here you see a representation of a water distribution network. So the major challenge, one of the major challenges is that the pipe network is underground, so we are not able to see where the leaks are. It's not visible, and it's only accessible through a couple of places, which are spread around. And one of the accessibility point is the fire hydrant, which we are dealing with, and where we connect our sensors. And additionally, the physics of the failure is not properly understood. So although the research has been going on for like more than 4 decades, but the failure is not properly understood. Even a lot of work has been done on a straight section pipe, like finding a leak in a straight pipe. But when you come across finding a leak in a network, it becomes very complicated mathematically and physics-wise. So overall, leak identification is categorized into 3 different problems. The first one is detection. So in detection, you actually ask the question if there is a leak in the network. Okay, and if the answer is yes, we go to the next question and we try to find out the localization, and we ask the question, where is the leak in the network? So the answer to that we are trying to look at is a smaller confined area, or actually a pipe segment, which could be from 10 meter to 50 meter, let's say. And once we have that, we can actually, we have a smaller area where we can work around. And the best solution for this would be the pinpointing. So pinpointing the leak, where exactly the leak is in the entire network. And that's what we are looking at, finding the specific location of the leak in the entire network. And it's not an easy problem because of the complication in the network and wide network. So through the advanced algorithms based on the probabilistic methods and signal processing, we are able to localize and actually pinpoint in a lot of cases where the leaks are. What I will be telling technically is like for a smaller segment of the network. So what you see here in the black circles are the hydrants, and we access those hydrants using our custom-built hydrophone-enabled leak monitoring devices. These devices are built through our collaborator digital water solutions, where we have hydrophones, pressure sensors, and an inbuilt computer which actually measures the acoustic data inside the water column. So we listen to the leak sound inside the water column through these devices, which are attached to the hydrants at several locations. So using a lot of signal processing and probabilistic methods, we have been able to actually detect and actually localize. We use a estimation method, a maximum likelihood estimation, which is a well-known method for localization in wireless systems. We are using that in leak localization in our civil engineering practices. So this has a lot of potential and a lot of impact when it comes to finding the leaks, especially in the dry areas like California and Arizona, where water is a big, like a useful resource, and we cannot just let it go waste. I'm not going through a lot of technical details, but I'll just say, if you want to go into technical details, we have submitted our results in a Journal of Pipelines Engineering and Practice, where we are discussing a lot of signal processing, acoustics, and there are some innovative approaches that we have used to localize and pinpoint the leaks in the water distribution networks. Finally, I would like to thank US Navy for their ESTCP program for funding this research, and Dr. Roya and Marshall for their contributions, and my professor, Sriram, and the collaborators, Digital Water Solutions, for all their support. Thank you.
Well, thank you, Pranav. I'll start with a question. So I'm curious, is finding the leak kind of like the hardest part of the problem? Is once you find it, how easy is it to repair like a leak in a network like that?
So I would say finding the small leaks is like finding a pin in a haystack problem. So it's a big network. So finding the problem is the hardest part here. And then once you're able to find, then we can go ahead and send the maintenance guys, and they can repair it.
Okay. And do we have any audience questions?
Hi, nice talk. You had mentioned working in Florida, but you're at UCLA. Do you optimize for areas with more drought risk in your work? I would think those cities might be more interested in this sort of technology.
So that picture was from another media article, and just to show the severity of the problem. But we are working mainly out of California, and we are doing a demonstration project in California, in actually a site at the naval base, and we are actually demonstrating this the method over there, and we are actually getting promising results. So hopefully you will see some wonders soon. Thanks.
All right, thank you for the talk. It was very interesting. We have a couple questions from our live stream. The first one is from Rick Lovett. He's asking, can you give a general explanation of how the leaks are detected acoustically? I'm writing for a scientifically literate audience. Also, how are they localized?
Okay, so scientifically speaking, when you're having acoustic signals, let's say a time signal in acoustic domain, so we collect the pressure data, and we see with leak and without leak, and when you compare them, like one of the simplest way is actually to compare the RMS values of the overall the time signal or the pressure signal actually. And that's how detection works. But then there are more advanced algorithms which we have developed, and apart from that, in localization, we are using we are actually discretizing the network using graph theory and using signal processing methods, which include cross-correlation based methods where we are using time delay of arrival and using that to localize and pinpoint the leak. Thank you.
Sure, I have two more. I think this one follows up on that one in a way. It's from Maura Shapiro, and she's asking, how quickly does the system identify leaks?
That's a very good question, and that's what we are working at right now. Right now, the methods which are in place, they actually are trained through data, and they take some time. But through the methods that we have developed, what we feel is that they actually are able to quickly detect. As soon as the leak appears, we would be able to detect and localize. That's what we propose, yes.
That's amazing.
Thanks.
One more. I think you may have touched on this already, but I'll just ask because it's in the queue here. Sure. But have you implemented this process in a physical network?
Yes. So the picture that I showed you over here, this picture is actually from Naval Base in California. And we are actually instrumenting these devices over there and testing over there, and we are actually getting promising results for localization and detection. Yes.
All right, one more has popped in since just a second ago here. There we go. It says, so you're passively looking at pressure changes. I guess that's the question. So you're not sending some acoustical signal that you're generating yourself into the pipes? That's
a very good question again. So in this phase of project that we just completed, we are actually doing passive sensing. We are not sending any signal, and we are listening to the leak signal. And that is actually a big problem. So if you have PVC pipes, the leak signal can actually attenuate. The next phase of this project is actually the active side of the acoustics, where we are actually installing a transmitter in the pipes, where we are going to send some active signals, which are going to interact with the leak, and we are still working on it. Thank you.
Okay. Well, thank you, Pranav, and we'll be back in one moment with our next presenter.